Kia ora, Year 12 and Year 13. Here's question 1, part D and E from last year's complex numbers paper. So this first question, which is back up here, is a merit question, and it should be a pretty familiar format. We're given a cubic equation here, and we're told one solution. And we're told that B is a real number. So we're going to use the conjugate root theorem, and we're going to figure out what B is, and also what the other two solutions of the equation are. So for some of this where it gets tedious, I'm going to pause the video and do some of the algebra, but mostly I'm just going to talk us through it. So we want to explain the conjugate root theorem a little bit. So we're going to say this: if B is real, so since B is real, the conjugate root theorem applies. And that means that Z conjugate is equal to -2 plus I is a solution. So the way we're going to approach this problem is we've got this cubic thing here. We're going to say Z cubed is equal to this times this times this. Now we've found two of the solutions, so we're going to work with those together here first and multiply them out. Right, so let's look at what we get if we have Z minus -2 minus I times Z minus the conjugate, -2 plus I. Right, so this pattern should be very familiar. It's minus, well, let's clean it up first. We don't want to be working with all those brackets and brackets. So it's going to be Z plus 2 plus I times Z plus 2 minus I. So we can think of these together. And we get Z squared plus 2 plus IZ plus 2 minus IZ plus 2 plus I times 2 minus I. This is the same pattern we get whenever we use the conjugate root theorem. So this should feel pretty easy if you've done enough practice during the year. So we've got Z squared plus, now here we've got a plus IZ and a minus IZ. So they go, leaving me with plus 4Z plus, here we get 2 squared, 4 minus I squared, which gives me plus 1. Right, so Z squared plus 4Z plus 5. So now we're ready to finish off our factorisation. We can write Z squared minus 2Z squared plus BZ take away 30 is equal to my quadratic factor times a linear factor, which I'll write as just Z minus K. There are several ways to do this. The easiest is probably now to match up the constant term. So this -30 comes from 5 times -K, what we get when we expand that out, telling me that K is equal to 6. Right, so we can now write out that cubic as follows. So we've got the quadratic bit times our linear bit. And just check again, when we go plus 5 times -6, we match with that -30. So we know that we've got our three solutions now. The last thing we've got to do is to find the value of B. And we do that by expanding out this side. And this gets us Z cubed, and we've got plus 4Z squared minus 6Z squared, which is -2Z squared. Now we should just check that that matches what we're meant to have over here. If it doesn't, you've done something wrong. The next bit is the plus Z bit. So here we've got plus 5Z, and we've got minus 24Z minus 30. So I end up with Z cubed minus 2Z squared minus 19Z minus 30. So we can finish the problem off by writing down the other two solutions. The other two solutions are Z equals 6 and Z equals -2 plus I, and B is equal to -19. Okay, so that's the merit question, which in some ways is quite a lot of work for a merit. mark, but the thinking involved is pretty predictable. So now we're going to look at the excellence question, which is a locus problem. So we're asked to find the Cartesian equation of the following locus. So the distance between a point z and -2 plus 7i is equal to twice this distance. The easiest way to do ones like this is to use our substitution and do it algebraically. So let z equal x plus yi. Now we're just going to substitute it in and do a bit of manipulation and end up with the equation of a circle. Okay, so not much intuition for this one, unfortunately. It's quite hard to show this geometrically, so I'm going to leave it to try and keep the video to under 10 minutes. Right, so let's start off by substituting that in. So that's my very first step. Now the next thing that I want to do is to group the real and the imaginary parts. So rewrite it as x plus 2 plus I times y minus 7 is equal to 2 times x minus 10 plus I times y plus 2. Now we use the definition of a modulus now, and we lose the I. So this is just doing Pythagoras to find the distance from the origin to a group of points. Next, we're going to square both sides. Be careful when you're squaring both sides. Here we're going to get 2 squared, which is 4. All right, now we have a bunch of expanding to do. So I'm going to pause the video and do that, and then come back to the recording. Okay, so I've expanded out both sides, and I'm going to collect everything up onto, in this case, the right-hand side, because I've got 4x squared and an x squared here. So we're going to subtract all of this to that side, leaving me with 3x squared minus 84x. 416 take away 353 is plus 363 plus 3y squared plus 30y. Now looking at all those numbers, I can see that I've got a common factor of 3. Remember, you can check that really easily. If you add those two digits together, you get 12, and then you add the 1 and the 2 and you get a 3. So that divides into 3. Same with this one. All right, 3 plus 6 plus 3 gives me 12. So some of those nice divisibility rules you learnt way back in year 9 still come in handy. So we'll divide each side through by 3. We get x squared minus 28x plus 121 plus y squared plus 30. Whoops, sorry, y squared plus 10y equals 0. Now the last thing I want to do is I'm going to complete the square on each bit. Right, because we want to end up with this form, x minus a squared plus y minus b squared equals k. So we're going to stick with the 0 here, and we're going to have x minus 14 squared. Now we've accidentally added in 14 squared, which is 196, so we take that out. We'll leave that 121 sitting right here. Now we do the same thing here. So we get y plus 5 squared, which is going to match up with my y squared and my 10y, but I've now added in 25, so I need to take it out. Oops, wrong pen. So that's minus 25. So what do we get when we clean all that up? Well, we've got 0 is equal to x minus 14 squared plus y plus 5 squared, and when we put all the numbers together, we get minus 100. Giving me my final answer, which is x minus 14 squared plus y plus 5 squared equals 100. So what does that look like? Because you might be asked to draw that sometimes. Well, that's the equation of a circle, but the centre is not at the origin. So the centre of that circle, drawn very badly, is out 14 here and down 5 here. And so that's the centre, and the radius of that circle is going to be 10. see how this goes. So there's 14 negative 5, so it's going to be a huge circle that goes off the page. The main thing it's centered here, and the radius is 10 units. So you weren't asked for that here, but it's good to be able to interpret the equation of a locus like that. So there you go. So that's the first question from last year's complex numbers paper. I'll do the harder parts of question 2 and 3 later on tonight. Thanks for watching.